Welcome to a read along with Dr. Powell in the book Discrete Perspectives in Mathematics. This is Chapter 3, Seeing the Magic in Polynomials. Polynomials can be very useful tools. So many things can be described in terms of polynomials. However, we will not look at applications right at first. Instead, we'll build up our tool of polynomials a little bit more, and then we'll look at some examples as we go throughout this whole text. What is a polynomial? First of all, polynomial, here's some examples. It's a sum of powers of x that has coefficients with it. Now, in applications, these coefficients could be positions in a list, or x itself could represent an object. And maybe perhaps we know something about this object. Maybe we know a polynomial that where it can be plugged into, and the result would be 0, perhaps. That actually enables us to have a situation where we can merge things together in a way that preserves addition and multiplication and analyze our object even further and get a lot out of it and have a lot of power with it. So just as we've seen merges before with power sets, and that helped us study logic as long as we were preserving structure, we're going to be talking about what it means to merge two polynomials together, and under the assumption that we're preserving structure like addition and multiplication, and seeing what the fibers will look like. Okay, so let's look at some notation. This right here means the set of polynomials with coefficients in R. So for instance, these polynomials right here have coefficients in the real numbers if we let R be the real numbers. R is just a set denoting this where the coefficients are going to come from. And we choose one such that polynomials would make sense. Namely, we need addition and multiplication structure to be in R in such a way that our polynomials will make sense. Okay, so let's look at an example, and we'll build this one up a bit. When we want to merge two polynomials together, namely the 0 polynomial, there's lots of different ways of thinking about the 0 polynomial, 0, and maybe the polynomial x plus 3. Okay, so right here, let's suppose we want to merge 0 and x plus 3 together, and let's consider the fiber 0 bar, and we want this merge to preserve addition and multiplication. Then, in particular, 0 bar, since 0 is equal to this as well, we could write that. But we could also write this, because we can take the addition and subtraction after the merge, because it's preserved. Or we could even do this, 0 and then x to the 5th, 0x squared, and 0. This enables us to see 0 bars here. Now we know what 0 bars are replaceable with, because x plus 3 and 0 merge to the same place. It's replaceable by x plus 3 bar. So we'd be looking at something like this. In other words, this right here is the same as this if we replace all our 0 bars with x plus 3 bars. But now, since the merge, which is represented by bars, or taking chunks with the bars, preserves these operations, we can do the operations after, but we could also do it before. So we can extend the line over, which tells us that this element right here, this polynomial, also merges to 0. So we can get a lot of polynomials that merge to 0. Now, let's keep going. And let's think about how we can get a lot of polynomials that are in 0 bar. What if we take a look right here and think, okay, we have 0 bar is equal to 0 is equal to this, and it can split across the multiplication. Now we can replace 0 bar with x plus 3 bar, right? And extend the line a little bit further, which means that x plus 3 times any polynomial is also in 0 bar. So basically any polynomial multiple of x plus 3 is inside of 0 bar. Let's look at another fiber, maybe the fiber that contains 2. Now, we know that we can write 2 as 2 plus 0, and that's nice, because we can replace 0 bar with this, and then throw the line back over everything. And notice that a shift of 2 from any multiple, so an additive shift, so adding 2 plus any polynomial multiples of x plus 3, so x plus 3 times any polynomial, is going to be in 2 bars. So we're finding out sets of things that are contained in our fibers. Now, we can represent this in the following way. So this set right here, we could represent like this, 2 plus, this just means the set of all polynomial multiples. So, or 2 plus polynomial multiples. So this is like the option, this is all of the polynomials that are additive shift of 2 away from a polynomial multiple of x plus 3. And that's going to be contained in this fiber. So necessarily, using the idea that addition and multiplication are preserved, necessarily we have that this is contained in that fiber chunk. We also know this is contained in that fiber chunk. And using a similar idea, we even know that any polynomial plus additive shift away from the multiples of x plus 3, polynomial multiples of x plus 3, are actually contained in a of x bar. For the exact same reasons that we were seeing up here, thinking of, throwing bars over and replacing. So think of this a of x plus 0 and replacing it with that and throwing the bar back over, we get the exact same thing. So this whole set right here is contained in that one. All right, here's an example, x squared plus x minus 1 bar. So we're thinking of this as in place of a of x. Now, if we do a little polynomial division here, we get a nice statement. X, the divisor x plus 3 times the quotient x minus 1 plus the remainder 5 is equal to a of x. So it means a of x is equal to 5 plus, hey, look, a polynomial multiple of x plus 3. And guess what? Polynomial multiples of x plus 3 are in 0 bar, and we can throw bars over and off and so forth until we actually see that actually this is 5 is in the same fiber as x squared plus x minus 1. So these guys are in the same fibers, in this exact same fiber. Okay. Now, in particular, notice what we did. We divided by x plus 3. Guess what the remainders are when we divide by x plus 3? They're all real numbers. Okay, they're just constants, right? Because the degree of this is 1, the degree of that remainder will be less than that, so it will be degree 0. So we just get constants. So it almost looks like this will contain all the fibers, because every single polynomial, at least with this particular merge, has a constant representative. There's a constant in every single fiber, and that can be seen by this division process, because we can always get this remainder here is always in the fiber itself, and with this being degree 1, we definitely get constants out. So, but is it true that two constant fibers that are where the constants are different, are they going to be the same fiber? Is that ever possible? Well, we're going to study that. So we're going to think about 2 different merges. The red merge is the merge we're concentrating on right now, the one where we're preserving addition and multiplication, and 0 and x plus 3 go together. The blue bar, let's just let this strictly be just this merge of where we get chunks just of just of the guys or just of the things that that we found were necessarily in each of these red chunks. So we knew for sure that these guys, like all of these guys, were in each red chunk. Now we didn't quite know if that was everything quite yet, but we know at least that these guys right here, or this whole set, is contained in there. So the blue chunks might potentially be smaller than the red chunks. All right, and we don't know if the blue chunks actually preserve addition and multiplication. By minimality assumption of red bar, assuming that it's the minimal chunks that actually give us a preservation of addition and multiplication. If we were to show that the blue bar chunks actually preserve addition and multiplication, or induce kind of an addition and multiplication operation in the codomain of the merge, then we'd be good. Then we'd actually know, because of the minimality of this red thing, that these merges would be the same. Now that would be kind of nice in this case, because the constants that we're getting are remainders. And when you divide by x plus 3, how many remainders do you get? You only get one per polynomial, which means that every polynomial has exactly one constant fiber to go to, not two, just one. Meaning that this would be, if we're defining this so if we're defining these bars in this way, and we can reduce them to remainders, the remainders will uniquely determine where we're going. Okay, because there's only one remainder we can get. We can't get two, and it'll be unique per polynomial in that division process. Okay, so that's kind of where we're after. Let's show that blue bar actually preserves multiplication and addition. Now, let's remember and go back to another section here. We're going to go and look at where we were learning about preserving addition structure in Z in section 1.3. So we had this little picture where we had some operation here, and we wanted to, and P represented the codomain of the merge, and we wanted to somehow create an operation over here. Now to do that, we were looking at a commutative diagram and wanted to complete that diagram. Now, in order to complete that diagram, we needed certain boxes or fibers to fit inside of other ones in order for this to be induced, for there to exist such an operation in the codomain. So all we need to do is show that those different fibers fit in the ways they need to. Now, the crux of this argument, or of what we need to show, was basically the fact, and we'll kind of go forward to where we are currently, which is right here, is this idea. We need, so if we can replace any here, if we can kind of throw in anything that's in A of X bar and anything in B of X bar, and show that we have that in this statement, we can with this addition, with adding these bars, that we have, if we throw anything here and anything in here, and we kind of change this A of X and B of X with anything in A of X bar and B of X bar, if we always get the same thing over here, so if this is always the exact same bar, blue bar, even if we change A of X and B of X according to different things that could be in here and here, if we always end up getting the exact same thing here, then that commutative diagram would work. We would be able, the boxes would fit in, we'd have an induced operation. So that's, and it would be preserved. We'd know that addition was preserved similarly for multiplication. So really all we need to show is that this guy is always the same thing, and this guy is always the same thing, no matter if we change representatives for A of X, B of X, And that actually shows that the operation would be preserved. Just changing representatives, we still, it doesn't change this bar. So the representatives for a of x and b of x won't change this bar. That's enough. That's all we need. So we can go ahead and think of generically how to, we defined what blue bar was in this sort of way. This is the way to get all the things in blue bar. That's the thing to get, that's the way to get all the things in a b of x bar. So we can look at adding things. So what would be under the big blue bar here, right? If we want to replace a of x with something like this and b of x with something like that, throw the big blue bar over and look at it, we end up getting, looks like we end up getting this. Hey, and look, since this is in 0 bar for sure, we, see, so we end up looking at this right here, and we've actually shown that, see, what is this? By definition of the blue bar, what is the definition of blue bar? It means you take this guy and you add it by a multiple of x plus 3, a polynomial multiple of x plus 3, and it's in the same thing. Oh, so by definition then of how we define blue bar, this actually, if we put a bar over, is the same as this, which is exactly what we wanted to show. So we know that addition is that this bar, blue bar, preserves addition, and similarly, it preserves multiplication. Knowing that, blue bar will be equal to red bar, just as we described. So having the merged blue bar was, so the fiber chunks right there, that was what was necessarily in the red bar chunks. And then we showed that that was sufficient for what needed to be in the red bar chunks, by showing that the operations of addition and multiplication were actually preserved. Okay, some notation. Quotient notation. So if we have a set and we're merging things together in such a way that each fiber is an additive shift of 0 bar, which is exactly what we were just seeing. Let's take a look at that and just see. So in fact, we just showed blue bar was equal to red bar, so the definition of red bar will work here. Notice now this bar right here, or this fiber, is an additive shift of this set. Now this set is the same as 0 bar. Multiples of polynomial multiples of x was 3, that is 0 bar. We showed that this is what it would be in blue bar, and blue bar is equal to red bar. So this actually is 0 bar. So we have 0 bar plus a of x, or all the so take anything in 0 bar and you add a of x to it, and you do that through all the elements in 0 bar, and you get a of x bar. So all of these are shifts. So this notation specifically is for situations when we have a merge with shifts of 0 bar. So if 0 bar has a name like h, then we could write this out like s, it almost look like s over h, or s divided by h, or s over h here. And this is the collection of all the fibers that are additive shifts of h. So in our particular case, this is 0 bar, and all the other bars are just additive shifts of this one, something plus this guy. And in particular, like, what's 2 bar look like? 2 bar looks like just 2 plus that set, 0 bar. What does x plus 10 look like? X plus 10 plus that, 0 bar. It's just that guy shift added to that one. All right. So that concludes little subsection 3.1.1. And next, in the next section, we'll be looking at the process of taking a polynomial and figuring out what's a simple representative for it in its fiber when we do a merge. Thanks for watching.